All right. Hello, everyone. Thanks for choosing this talk. And thank you all for coming. Thanks to LambdaConf for this opportunity and for this amazing conference. I'm Elabidine, a Scala developer at Moya, and in my free time, I'm a contributor on ZIO, and I'm the #1 fan of John de Goss. Today, I'm going to talk on which kind of problems that we can solve using ZIO by example. First of all, I want to talk about how functional programming approach deals with effectful programs and the idea behind the functional programming Scala libraries. And then I will take you in a journey of the hotel H&A that encountered a problem that we are going to solve using ZIO. Functional programming is a style of organizing your code, and if you are using imperative paradigm and you are interested to use functional programming approach, you have to think differently, and you are going to change your way on implementing code, because functional programming is a declarative paradigm in which programs describes the what to do and what we want to achieve, and it separates between the data and its behavior and its functionality. And in functional programs, we express everything using functions. And we are going to have like a flow of data, and in order to change the behaviors of our data, we will pass them through those functions. And the fundamental concept in functional programming is to have pure functions, which means we want to get what we expect from our functions. And we can know what the function does when we see the input and the output types. And we can easily test our pure functions because it is deterministic, which means every time when we call our function with an input, we want to get a result, and every time when we call it with the same input, we want to have the same result. And a pure function have to be free of side effects, which means the output result should be computed using the input and without interacting with the outside world, and we have to only use the input. But what if we want to communicate with an API or interact with the database or write in a file or print out in the console? So we need to do that. Actually, we need effects, because programs without effects are useless, right? We need to interact with the outside world. So how could we implement purely functional code without interacting with the outside world? Well, functional programmers deals with effectful programs by describing them in immutable data structures. And the difference between the imperative paradigm is the imperative programs, we want to have a bunch of statements, and each statement will be executed right away. Just you call it, and we want to interact right away with the API, etc. But the functional programming approach, we want to describe our effectful programs inside an immutable data type, and we want to have an immutable value that contains our description of our program. So we can pass a program as an input for a function, and we can return another effectful program as an output from our functions, and which we cannot do that with the statements. We cannot pass a statement around the function, and we cannot return a statement, right? So here is the difference between the description and executions. At the end of the day, we need to interact with the real world, so we need to interpret our data type, which describes our effectful program, and we need to have an interpreter. In Scala, we don't have a standard data type that describe effectful programs. That's why we have functional programming Scala libraries like ZIO. ZIO is a zero-dependency Scala library that helps us to deal with effectful programs and to build asynchronous and concurrent applications using purely functional approach. So ZIO has different types to describe different type of effects. As a simple example, we can make an effect that, for example, here we describe print line, and print line will never fail. So we want to describe an effect, total effect that will never fail, and we return a unit because we want to only print line the string and interact with the console. But this is only a description. And the same here. We read from the console, and we want to return a string. This is a description of an effectful program that will interact with the console. We can also compose effects. And UIO has flat map and map, so we can use for comprehension, and we can use the result of each effectful programs. And at the end of the day, when we want to execute our effectful programs, we can extend default runtime, which is provided by ZIO, and we can call unsafe run. Otherwise, you can also have this functionality automatically by extending ZIO.app. So now we understood what is the idea behind having functional programming libraries like ZIO. And in order to understand more and to see more data types built on ZIO and which kind of problems that can solve, let's see an example. A business problem that the hotel H&A faced. In this big hotel, there was a conference in the last floor, and there was many attendees, hundreds of people that used the elevator. Suddenly, the elevator changes its behavior due to a race condition. And some passengers are blocked in the elevator, and some of them took the stairs. It wasn't a fantastic day for the attendees. So the H&A team decided to change to modern elevators. And they specify a bunch of requirements. They want to have 4 modern elevators in which the passengers can enter their destination before pickup. And the system decides the convenient elevator that the passenger can take. And obviously, the elevator takes T period of time to move up or down. And the selected elevator shouldn't violate its next stops. It shouldn't suddenly change its direction if it has more stops in the other direction. And the elevator system should always keep listening to the upcoming requests. So now we have the problem statement. Let's think functionally to solve this problem. We want to have an elevator system with n elevators and infinite number of requests. Each elevator has a state which contains the current floor and the stops. And every request contains the passenger's floor and their destination. So we want to have an elevator system with elevators and requests. And for each elevators, we want to have a state. Let's start with the state data type. The state would have the current floor of the elevator and the stops. The elevator state contains distinct stops. That's why the stops is a set. When the elevator is moving a floor to that exists in the stops, we should remove this floor from the stops. We can define the direction of the elevator by the stops. If the next stops are greater than the current floor, it means that the elevator is going up. If the next stops are lesser than the current floor, the elevator is going down. And if the elevator is stable, if the next stops is same than the current floor, and if there is no stops, it means that the elevator is free. Now let's see the request. The pickup request would contain the current floor where the passenger is and the destination of that the pickup floor. And the behavior of the request, the pickup requests are sent to the elevator system, and the elevator system will handle the pickup requests. Let's understand it more. The passenger will select its destination floor, and a request will be sent to the elevator system. And internally, the elevator system will search the best elevator that can serve this request and will answer the passenger which elevator can take, and then the passenger will take the elevator. It sounds like the request would be a queue, because when we will add a value and then when we will take it, we have to remove the requests to serve the next requests. So our elevator system has a list of elevator states and a queue of requests. But we need to preserve the state of the elevator. We cannot use list. And the requests, we want to handle those requests asynchronously. If the elevator system would keep listening to the upcoming requests, even if there is no requests yet, but once there is a request, it should be performed right away. So we need an asynchronous queue. Let's see which data types on ZIO that can help us to solve this problem. Let's think about our effectful program. How could we describe our programs? The actions that we want to do is to move the elevators, right? It would be an effectful program that will update every time the state of the elevators. But actually, we want to move the elevator, we want to change the state every time every t period of time, which means we need a clock. And because we are thinking functionally, we have to describe this. So there is a data type on ZIO called ZIO of clock. We can call clock as an external service that we want to use, and it will never fail because our effectful program will never fail, and we return a unit. In order to handle requests, we need to handle that infinitely. We don't need a clock to describe this, and it would be an effectful program that we return a unit. And the same for send requests. Now let's think about the elevator system. Which type that we can use for the elevators? In order to preserve the state, we need a type that's built on ZIO called ZIO-ref, which models a variable, a mutable variable that could be atomically updated. And in order to create a ref, we can call make with the initial value, and this will return a description of an effectful program that will never fail and describe this variable. We can read the current state or set a new value, or you can atomically update the value by using the old state, or you can modify. This function will update the state and return a computation. So when we will create our elevator system, we want to make a reference to create our state with the initial state. For example, we want our elevator start with the first floor with empty stops. We put that initial state and we create our elevator system. We will finish this implementation later. Then we want to update the state of the elevator step by step, and this step function would check if the elevator is moving up. It would increment the current floor. If it's moving down, it would decrement the current floor, and it will update the state. And also we need to update the elevator state when we will select the best elevator to serve the given request, which means we will update the state and we will add the stops in the current floor of the passenger and the destination floor. Now we solve the first type for elevator state. Now we need an asynchronous queue. In ZIO there is a data type called queue, which is an asynchronous queue which allows us to add elements and remove in first in, first out way. The basic operations in queue are take, that will remove element from the queue and return the current value, the oldest value, and offer will add new value to the queue. Now let's think which type of queue do we need. We want to accept infinite number of requests. It sounds like we need an unbounded queue without limit. But actually, when we will accept many requests, imagine if there is many requests, so the elevator system have to perform them at one. It would be a heavy computation. And bounded provide us a back pressure strategy. We can use bounded for this to specify that this queue can accept, for example, 10 requests. And if there is more than 10 requests, we will have suspended requests waiting for a free room in the queue, and then they will be performed. Now we can create our elevator system using queue and the ref, the state. And when we will send a request, we want to call offer to add this pickup request. And when we want to take our value, the request, we can call .take, requests.take. Now let's think about how to move elevators, how to update the elevator state every period of time. How could we do that? We can use ZIO schedule that can repeat actions or retry actions in event of error. In our case, we don't have event of error. Our program will never fail, and we want to repeat action. So we can use repeat in UIO, and we will repeat our computation for every movement of the elevator. Every 200 milliseconds, the elevator wanna move step by step, but oh, it would be very fast. So let's move the elevator every 2 seconds. Cool, now let's see the solution. As we see, move elevator would update the state. And when we want to handle the requests, we want to take the request and we want to search the best elevator that can serve the request. And we will add the stops of this request. And we will run this forever, because this describes that handle requests will listen to the upcoming pickup requests. And we want to run this in parallel. We will move the elevator, and in parallel, we will handle the requests. But here, in case if there is no available elevator to serve this request, the state will never change. This is bad, because the passenger would expect a result, and we want to ignore this request in this case. We need to implement like a recursive function that when there is no available elevator, do that again and check. And in case of none, do that again and check if there is now an available elevator that can serve this request. But imagine if the state, because move elevators and handle requests would be executed in parallel, right? And imagine if the state will be updated here, and here would check the current state, but the current state wouldn't be recent in some cases. We wanna face a race condition, and this would be tricky to solve. So we need other solution for this. What we want to do, we want to check if there is no available elevator yet. We should wait until the elevator state changes, so we can load again and retry and check if now after the change of the elevator, if it's okay, there is an elevator can serve this request. And if not, it would be suspended and wait until the move elevators will change the elevator state, and the same process would be repeated. This is tricky to implement, but ZIO thought about this, and we have a ZIO STM data type that can solve this problem, the software transactional memory that gives us the ability to atomically perform a series of reads and writes on transactional memory when a set of conditions are satisfied. And STM is a transaction that can fail with an E, succeed with an A, or retry. In case of retry, this transaction will be suspended whenever the transactional memory changes. The transaction will retries. And this is exactly what we want to achieve. And at the end, when we have our transaction, if we want to atomically perform it, we can call stm.atomically, or we can call the transaction.commit. So now let's think about the elevator state, because what we want to do is to keep the elevator state up to date, and this is our problem. How to solve it? We want to make it possible to do that in a transaction. So we need a type, tref, which could be read and written inside STM transaction. So our new elevator state would be STM tref of list elevator state. And tref has the same method as ref, but the difference is that when we will make a tref, we want to have a transaction now, and the method, all the method would return a transaction. And now, when we will make our tref with an initial state, we should commit this transaction, and we can create our elevator system. And move elevators now should be a transaction. And we can update our state using update. It's the same method, but the difference now, we want to have a transaction instead of an effect. And now, the solution of the tricky part to select the best elevator and to retry until having an available elevator that can serve the request is, in case if there is an elevator, we will succeed the transaction. Otherwise, we want to retry the transaction. Just when we say retry the transaction, this will wait until move elevators transaction will be updated. The whole transaction select best elevator will retry the whole process until there is a best elevator that can serve the request. And now, when we want to handle the request, we will keep taking from the queue and select the best elevator for that request and commit that transaction and do that forever. And now, when we want to run the elevator system, we just commit the transaction of move elevators and repeat it every period of time. And in parallel, we want to handle our requests. And at the end of the day, we want to call unsafe run system.run 2 seconds and in separate thread, or in ZIO, we are using fibers, and this will be executed concurrently. And that's it. It sounds very simple code and solve a very tricky problem. And now the passengers have a fantastic day. If you are interested to check out the elevator system code, you can check out the repository. And also, if you are not using yet ZIO, you can check out ZIO repository, and you will find more documentation in ZIO.dev. Thank you all for your attention, and follow me on Twitter.